In this lecture series, we'll learn about two new classes of electrophilic addition reactions of alkenes, those that proceed through three-membered ring intermediates and those that proceed through concerted pathways. The reactions that we'll see in these videos are organized according to their mechanism, so all of the reactions that follow the same pathway we'll see together in each video. In the last chapter, we saw the additions of acids or HX compounds to alkenes. Alkenes can also undergo electrophilic addition reactions with other electrophiles. And when that electrophile is a halogen, an X2 reagent like chlorine, bromine, or iodine, then a three-membered ring halonium ion intermediate will form. The final reaction product in this case is a dihalogenated product where we've added both halogen atoms across the alkene, or we've added a halogen atom to each carbon of the alkene. Let's look at how that happens. In these reactions, the alkene is the nucleophile and the halogen is the electrophile. The alkene attacks the chlorine to form a new carbon-chlorine bond. And when this happens, the lone pair on the chlorine attacks the other carbon of the alkene. This is the carbon that would become the carbocation, but here instead that chlorine lone pair attacks to form a three-membered ring with the chlorine in it. We call this a chloronium ion, or more generally a halonium ion. And as this ring forms, the carbon-chlorine bond breaks to release a chloride anion. This chloride anion then attacks the carbon to open the ring. And here both carbons are identical, but if they were different, the chloride would attack the carbon that is more substituted. This is the carbon that will be more electrophilic. The electrons in the carbon-chlorine bond then move to the chlorine, and the resulting product is a dichlorinated alkane. Now let's look at the stereochemistry of these additions. Reactions that proceed through a halonium ion intermediate will lead to anti-stereochemistry. Let's look at what that means here. We'll start with the same steps. The alkene will attack the bromine, and the lone pair on the bromine will attack the other carbon of the alkene to form a bromonium ion. The bromine-bromine bond breaks to release a bromide anion. And when this initial nucleophilic attack by the alkene occurs, it can occur from either face of the alkene, meaning the bromine of the bromonium can add to the top face of the alkene or the bottom face of the alkene. And in each case, the two carbon-bromine bonds of the bromonium ion must be on the same face of the ring, or cis. Now in this example, the two bromonium ion intermediates are identical, but they won't always be. Then the bromide attacks the carbon to open the ring. And when the bromide attacks, it inverts the stereochemistry at that carbon. The bromide attacks from the side opposite the leaving group. And here the leaving group is the bromonium ion. So the bromide attacks the top carbon and it forms a new carbon-bromine bond on the face or the side of the ring opposite the bromonium. It pushes the hydrogen forward. The new bromine-carbon bond is back. The stereochemistry at the bottom carbon, the one that wasn't attacked, stays the same. So the bromine remains pointing forward or out. And this backside attack, as it's called, leads to anti-stereochemistry in the dihalogen product. The two halogens, here the two bromines, will always be on opposite faces of the ring or the structure. The bromide anion can also attack the bottom carbon of the bromonium ion, and this gives us the product drawn in blue. Again, this leads to inversion of stereochemistry at the attacked carbon. The hydrogen pushes back and the bromine is forward. The top carbon remains unchanged, and now we get the other trans or anti-isomer of the product. Again, the two bromine atoms are on opposite faces of the ring, but it's a different stereoisomer of the first product we drew in red. These two products are enantiomers. So in these reactions, the anti-product will always form, and the product will form as a mixture or a pair of enantiomers. Now in our previous examples, the bromide ion served as a nucleophile to open the ring. If we have water around as a reaction solvent, then water will act as the nucleophile and will open the ring, leading to the formation of an alcohol product. Okay, let's take a look at how that happens. The formation of the bromonium ion will occur just as it did before in our previous examples. The alkene will attack the bromine, the lone pair of the bromine forms the ring, and the bromine-bromine bond breaks to release the bromide anion. Remember that the alkene can attack from both the top and the bottom faces, so we have two different bromonium ion intermediates that are enantiomers. They are enantiotopic. From here, instead of the bromide anion opening the ring, now water will open the ring. And that's because when water is the solvent, we have so much of it around that it will easily outcompete the bromide. So water will open the ring, and it will attack the more substituted carbon, the carbon that would better stabilize a carbocation. That's the carbon that will be most electrophilic, and so that's the carbon that will be most readily attacked by the nucleophile. Okay, water attacks. A new carbon-oxygen bond is formed and the ring is opened. Remember that the attack occurs by backside attack with the inversion of stereochemistry. In the last step, a base comes in, and that base could be another molecule of water, and that base deprotonates the hydrogen from the cationic oxygen to give the product. This sequence of steps will happen for each stereoisomer, meaning the reaction will result in the formation of both enantiomers of the product. One more note here is that other nucleophiles can act similarly to water, meaning other nucleophiles, if included in the reaction mixture, can also open the ring of the halonium ion intermediate. As an example, I have methanol here, and methanol is a nucleophile, so the oxygen of methanol can attack in the same fashion that water did. We could draw the directly analogous reaction steps, and that will lead to the formation of the ether product. The OCH3 group of the methanol will be incorporated into the product, just as the OH of water was incorporated into the product when water was the nucleophile. Okay, so let's try that. Go ahead and draw the reaction mechanism for this electrophilic addition reaction. As always, we'll start the reaction with the nucleophilic alkene attacking the electrophilic bromine to form the bromonium ion. We'll be sure to draw both stereoisomers of the bromonium ion intermediate. Then the nucleophile will attack to open the bromonium ion. And here the nucleophile is methanol. So the oxygen of the methanol, the nucleophilic atom of the methanol, will attack the more substituted carbon of the bromonium ion. The attack occurs with inversion of stereochemistry at the carbon that is attacked. The other carbon remains unchanged. In the final step of the reaction, a base, here maybe another methanol, will deprotonate the intermediate to form the ether product. Finally, we conduct the same sequence of steps on the other stereoisomer of the intermediate to form the other enantiomer of the product. One final reaction to see in this video forms an intermediate that is very similar to the bromonium ion. In an oxymercuration-demercuration reaction, a mercury compound is used and forms an analogous three-membered ring intermediate. That ring is opened by water to form the alcohol product. And let's look at how that happens in more detail. As we saw before, the alkene will attack the electrophile. Here the electrophile is the mercury atom, and the mercury atom also attacks the alkene to form a three-membered ring intermediate, a mercurinium ion. The mercury acetate bond breaks to release the acetate anion. Then water acts as the nucleophile and attacks the more substituted carbon of the ring to open the ring. A base will deprotonate the hydrogen on the cationic oxygen to give the neutral alcohol. And in the final step, the sodium borohydride reagent releases the mercury and replaces it with a hydrogen. Just as we saw with the ring opening reactions of bromonium ions, here also the stereochemistry will be inverted when the water nucleophile opens the ring.